let's explore Cauchy sequences and what it means for the real numbers to be complete. A sequence is called Cauchy if its terms eventually get arbitrarily close to each other, not just close to some fixed limit. In symbols, a sequence is Cauchy if, for every epsilon greater than 0, there exists a natural number, capital N, such that for all m and n greater than capital N, the absolute value of a sub n minus a sub m is less than epsilon. The Cauchy criterion states that a sequence of real numbers converges if and only if it is a Cauchy sequence. We prove this in two directions, starting with the first principles proof. First, the easier direction, that every convergent sequence is Cauchy. Suppose the sequence a sub n converges to some limit, capital L. Given any epsilon greater than 0, since the sequence converges to capital L, we can find a capital N so that for all n beyond capital N, the absolute value of a sub n minus capital L is less than epsilon over 2. Then for any m and n beyond capital N, by the triangle inequality, the absolute value of a sub n minus a sub m is at most the absolute value of a sub n minus capital L plus the absolute value of a sub m minus capital L, and this sum is less than epsilon over 2 plus epsilon over 2, which equals epsilon. So the terms get arbitrarily close to each other, confirming that every convergent sequence is Cauchy as required. Now the harder direction, that every Cauchy sequence converges, we prove this in 3 stages, first showing the sequence is bounded, then extracting a convergent subsequence, then showing the whole sequence converges to that same limit. Stage 1. Taking epsilon equals 1 in the Cauchy condition, all terms beyond some capital N lie within one of each other, and there are only finitely many terms before that point, so the whole sequence is bounded. Stage 2. Since the sequence is bounded, the Bolzano-Weierstrass theorem guarantees it has a convergent subsequence converging to some limit, call it capital L. Stage 3. Given any epsilon greater than 0, choose capital N so that terms of the original sequence are within epsilon over 2 of each other beyond capital N, and choose a term of the subsequence beyond capital N that is within epsilon over 2 of capital L. Then by the triangle inequality, every term of the original sequence beyond capital N is within epsilon of capital L, so the whole sequence converges to capital L. This confirms every Cauchy sequence of real numbers converges, completing the first principles proof of the Cauchy criterion. Now let's look at a genuinely different way to prove that a Cauchy sequence converges. This time we build the limit directly using repeated supremum and infimum, without ever extracting a subsequence. For each natural number, capital N, define U sub capital N to be the supremum of all terms, a sub n, with n greater than or equal to capital N, and define L sub capital N to be the infimum of that same set of terms. As capital N increases, the set of terms we take the supremum over shrinks, so U sub capital N decreases, and similarly L sub capital N increases, with L sub capital N always less than or equal to U sub capital N. Because the sequence is Cauchy, the gap between U sub capital N and L sub capital N shrinks to 0 as capital N goes to infinity. A decreasing sequence bounded below and an increasing sequence bounded above must each converge, and since their gap shrinks to 0, they converge to the same value, call it capital L. Since every term, a sub n beyond capital N, lies between L sub capital N and U sub capital N, and both of these squeeze onto capital L, the original sequence must also converge to capital L. This is a genuinely different proof, because the limit is built directly from suprema and infima rather than by passing to a subsequence. Now let's see why completeness genuinely fails over the rational numbers, using the square root of 2 as our example. Define a sub n to be the decimal truncation of the square root of 2 to n decimal places, so a sub 1 equals 1.4, a sub 2 equals 1.41, a sub 3 equals 1.414, and so on. Each of these terms is a rational number since it is a finite decimal. This sequence is Cauchy because for large n and m, the truncations agree on more and more decimal places, so the absolute value of a sub n minus a sub m shrinks towards 0. However, the only possible limit of this sequence is the square root of 2 itself, which is not a rational number. So we have found a Cauchy sequence of rational numbers with no limit inside the rational numbers, showing that the rationals are not complete, while the real numbers are.